Okay, so after examining the slope of the secant line, which corresponds to the average rate of change of a function over an interval, we look for the instantaneous rate of change of a function at a specific point. And in calculus, this is called the derivative. And the derivative is also representative of the slope of the secant line, the slope of the tangent line to a graph at a point. So below here on the right, you can see this is what we mean by a tangent line, right? It's a line that touches the curve at one instant and basically represents the direction the curve is going in, or the slope of the curve at that instant. And we have already explored the idea that it's the limit of the slopes of the secant lines as you move points closer and closer to the point of interest. Now we look at analytical ways of getting the derivative rather than computing them numerically. So we're going to start with this definition. This is the definition of the derivative at a point, and it should look familiar because you can see slope. You can see the average rate of change there. The addition of the limit is what's allowing us to find the instantaneous rate of change. So in the notation here we see is this little dash, and that's called f prime. So f prime of a is what one says. Okay, f prime of a. That represents the derivative of a function at a point. So the idea is you're going to move this x value closer and closer to a, and by doing that, your slopes of your secant lines start to become the slope of the tangent line, which might look something like this here in green. So I'm going to do my best tangent line. Tangent line should be going in the same direction as the curve. Those blue slopes, the closer you move x towards a, the closer the slopes of those blue lines approach the slope of the tangent line. So let's start with this example. Find the derivative of f of x equals x squared minus 3 at x equals 4. So we use our definition, and we say f prime of, so my a is my 4, and of course our f of x is x squared minus 3. So you might jot down, so a f of a in this particular case is 4 f of 4, but f of 4 is 4 squared minus 3, which is 16 minus 3, which is 13. So I'll say, notationally, I'll say f prime of 4 equals, so I'm going to write, it's the limit as x goes to 4 of f of x minus f of 4 divided by x minus 4. And so putting in the rest of the specifics, we get the limit as x goes to 4. F of x is x squared minus 3. Right, so I replace that with this. F of 4 we just saw is 13 divided by x minus 4. So that's the limit as x goes to 4 of x squared minus 16 over x minus 4. And at this point, I'm hoping you start to see we are now in a place where we should be familiar with the procedure because that factors, and now we can substitute. It's just that this is no longer a random limit problem. This means something. So you get 4 plus 4, which is 8. Okay, so that is the derivative of the function at x equals 4. That is the slope of the tangent line to the curve f of x at x equals 4. So this is, I'm going to write the slope of the tangent line to the curve exactly at x equals 4. That tangent line has an equation, and sometimes you're asked to come up with the equation. the easiest way to do that is to use this form of an equation of a line. This is point-slope form. And our slope is the derivative. Okay, that is the derivative. So in the previous example, it's f prime of 4. And x1, y1 is the point on the graph at the tangent, at the point of tangency. So the point in the last example we had was 4, 13, and the slope we just found was 8. So the slope of our equation of our tangent line is going to be y minus y1 is 13 equals the slope 8x minus 4. That is the equation of our tangent line. Sometimes you're asked for the equation of the normal line, and the normal line is just so the normal line is a line that's perpendicular to the tangent line. So our slope of 4, right, f prime of a, or f prime of 4, was our slope, and that was 8, okay, and that was the slope of the tangent line. That would mean that the slope of the normal line would have opposite reciprocal slope. Okay, so the equation of the normal line, it still goes through that point. So the 13 doesn't change, the 4 doesn't change, it just has opposite reciprocal slope. Okay, so basically in a curve, if the graph is going like this, right, and our tangent line looks like that, our normal line is just the one that goes like this, making a right angle. All right, so let's do an example of finding the derivative of a rational function. And the technique is going to be to find a common denominator once we use the definition. Okay, so finding the derivative of this function at x equals 2, so that would be f prime of 2, and I'm going to just give you the generic definition. It's f of x minus f of 2 divided by x minus 2. So that's going to be the limit as x goes to 2 of f of x, 5, minus f of 2. So actually, let me just jot down over here what the point is. F of 2 is 1, right? Because you plug in 2 into the function, you should get 1. So that's just minus 1 divided by x minus 2. So now we need to evaluate this limit. We can't plug in 2, so we get a common denominator for the numerator. So for instance, I'm going to rewrite this 1 up here as x plus 5 divided by x plus 5. And rather than writing the word limit over and over again, I'm just going to indicate here that I'm just going to basically focus on this part that it doesn't involve the limit. It's called the difference quotient is basically this fraction here. So it's 7, so it's going to be 7 minus x minus 5 divided by x plus 5, and dividing by, just note that dividing by x over 2 over 1 is the same as multiplying by the reciprocal. So I recommend doing that. The numerator becomes 7 minus 5 is 2, so it's 2 minus x. So I get 2 minus x over x plus 5, x minus 2. And this divides to produce a negative 1. So now I'm in the moment where I can bring back the limit because everything's simplified. And we plug in. Okay, so that is the derivative of f of x at x equals 2. That's the slope of the tangent line to the curve at x equals 2. This is another definition of the derivative. Okay, and this one I would say in the long run is probably the one you'll use most. So again, it's the concept is exactly the same. The concept is still we're trying to find the slope of the tangent line, which I'm going to indicate right here. Okay, that's the slope of that is the tangent line. It's just that this definition puts emphasis on this h, which is the difference between the 2 points, that represent the endpoints of the secant line. Okay, well we're going to make h go to 0. You know, when we cause this x value to go closer to a, h is going to 0. And that's what we see up in the definition. Okay, so I'm going to do an example using this definition just so you're familiar with it as well. So let's use the definition on the previous page to find the equation of the tangent line to the graph f of x equals x squared minus x at x equals 7. So remember, the equation of the tangent line is going to have this form: y minus the y coordinate of the point, which I'm going to indicate now here as f of 7, equals, now the slope is the derivative at 7 times x minus 7. So the point on the graph where we're building the tangent line is 7 f of 7. And if you plug in 7 there into f, you get 7 squared minus 7, which is 42. So our point is 42. So far, that takes care of a lot, right? Because we now know the equation starts like this. We don't know the derivative, so I'm going to put a blank there. So we got to go find the slope, which means we got to find the derivative. So let's do that over here. So f prime of 7 equals the limit as h goes to 0, f of 7 plus h minus f of 7 divided by h. Okay, using the definition on the previous page where our a is a 7. So again, let's just work on the what's called the difference quotient first, and then we'll plug in 0. Again, you can't plug in 0 now, right? You'd be dividing by 0, and the numerator is 0 if you plug in 0 for h. But in particular, in this particular case, f of 7 plus h is not x squared minus x, it's 7 plus h squared minus 7 plus h. And f of 7 we just found to be 42. So performing the algebra here, we get 7 squared, which is 49. So I'm not gonna go through the details too slowly. I'm gonna trust that at this point, if you're watching this video, you can expand that, and you're gonna distribute, and a whole bunch of convenient cancellations happen, because 49 minus 7 is 42, and then I'm minusing a 42, so that's gone, that's gone, that's gone. And then what I'm left with is every term that has only terms that have h's in them. So this is 14h plus h squared minus h divided by h. Now I can factor out an h. And when you do that, you get h times 14 plus h minus 1 divided by h canceling. And now remember, we were doing a limit. So this is the limit as h goes to 0. So the limit as h goes to 0 of 14 plus h minus 1. Putting in 0 there, you get 14 plus 0 minus 1, which is 13. And so that is the slope of the tangent line, because it's the derivative at 7. And there is my equation of my tangent line.